we were discussing geodesic equation and derive it at least three different ways. Today we want to derive it from the principle of equivalence, and the way we derive it, let us consider a particle moving freely under the influence of gravitational forces. So this particle, every particle, is moving under the influence of gravitational forces, then the equivalent principle says that there exists, you can construct a locally inertial coordinate system in which you can construct a locally inertial coordinate system such that, since it is locally inertial, there basically the laws of physics are those of in an accelerated unaccelerated coordinate system and are similar to those which you have in special theory of relativity. So you can basically write okay, in a locally inertial coordinate system XI, and you can always make a transformation from this locally inertial coordinate system to this laboratory coordinate system XF, and this is any other coordinate system which can be curvilinear, accelerated, or rotating, or whatever. So this is a laboratory coordinate system, and the freely following functions, coordinate functions, these are basically functions of these and vice versa. And these locally inertial coordinate systems, if the particle is free, you can write down following equation of motion. Is this clear? So what we are doing is we are applying principle of equivalence, and since we have applied principle of equivalence in the local inertial coordinate system, this equation of motion is simply this. That is a free particle. Now what we can do is we can write this thing in the following way. This is but d tau is IA d tau, that we can write it down as one second change. Since IA are functions of this arbitrary coordinate system, and from here you can write this plus tau therefore this expression is equal to 0. Now shall multiply this, we have to multiply this by LXD. Let's do this. So if we do this, then we shall get this is multiplied by this factor. So del xd del psi a del psi a del xb. By chain rule, this is nothing but del xd del xb, and that is equal to omega delta delta dv d2 xd d tau 2. But with the Kronecker delta, this will become d2 xd then This is dd tau of del xi a del x. Dx. Tau is x e this term multiplied by this term. Now, this we can write it down as, again we shall apply chain rule. So del xc. So ultimately we have del to xi a, del xc, del xp, dxc theta. And then we have already obviously these terms are there. dxd out, del xd. Okay, is it okay? So from here, you can immediately see that you can write this as 2xd 70 plus. Let me just this del x c or del x b del x c, because these are partial derivatives, therefore we assume that they commute with each other. So you can write del x c del x b is the same as del x b and del x c. And then we have del x b del x a. Then we have dxb d tau dxc. That is equal to 0. This is what we have to do. So starting from the equivalence principle, so we are assuming that the free particle is moving under the influence of only gravitational forces. Therefore, if you apply the equivalence principle, you can construct a local inertial coordinate system in which the equation of motion is just like it will be in special theory of relativity. And from there, if you just do the mathematics, you will end up with this equation. Where now you are writing the equation of motion of the free particle in a different coordinate system, x. What we shall now say is that this is my, so here you can see that A is at an index and three indices are D and B and C. So write this as this part is this, therefore this is equals D by 2 plus gamma E C. Yes. So you end up with the geodesic equation, the point connection. And also we have the following relation. I'm rubbing this part out. So I hope you have noted this down. Let us now look at the line elements. This was the line element as a special theory of relativity in the local inertial coordinate system. This you can write down as directly A, L, C, C, again change. Now note that this was flat, right? This was constant. -1 plus 1 diagonal. All other components are 0, diagonal components are 0. So this is a flat Minkowski metric. But now you can write this as GAB DXT DXT, where GAB GCD, sorry, this is GCD, where GCD nothing but this particular object. From eta AB this multiplied by this. So this is eta AB del xi A del C. We have this. And this is the metric tensor, the curved metric tensor. Do you have any questions? The IPSC students, if you have any problem, you can ask. Just go a little bit slow. Are you following the things? Have you followed the things? Earlier things? Do you have any doubt? Okay. Huh? Okay. You want to, it's fine. You are free to ask, don't? Because do you think that the material covered are already too much, or it is okay? It's okay, good. So, but today we shall try to go a little bit slow. Anyway, so this is the metric tensor, and you can see that we have actually derived the geodesic equation. But I also told you an important aspect is that equivalence principle means metric compatibility. So George was asking why. Why is equivalence principle similar, same as metric compatibility? So we shall show why is that true. So let us show it now. So here you can see that the Christopher connection is being identified with this thing. I have not written it down, but this is particular object. So let me use that equation, and here you note that AB are the indices, these are the three indices, but I shall write it with GAB as my three indices. So this is theta CD, there is IC, there is XA, there is IT, there is sync, right? And let us take the partial derivative of this metric tensor respect to XE. So if you take that, this partial derivative will not act on this because this is flat, this is 0, it will act only on these two terms. Therefore, what we shall get is L 2 IC, L X A, L X E, L ID, L X B. The first term, and the other will act on this one. So I can just bracket here. This will be del IC, say is X. So you get two terms. Now we have to just help me and achieve it by telling me what my gamma is. Tell me the expression for gamma. gamma dBc. Del 2 xi del xp del xc del xp del xs. Yes, right? So what I shall do is I shall try to replace this and this in terms of the gamma. So that is our aim. So if you do that replacement, you can do it here. You have to just keep track of the indices. So del 2 xi c a e. Just replace this by c a e. So let me do it. C a. You can do it yourself also. Please try to do it yourself. I am doing it on the board, and you can check it with my calculation later. So what I am doing is I replace this by C. I replace A by C, right? Or B by C? No, A by C. A by C. A by C. And what was these indices? B and C, right? B replaced, I replaced it by A and E. Okay. This should be C, right? So del 2 psi C, del x A, del x E. So you can straight away write the following: del 2 psi C, del x A, del x E equal to gamma write this x A E. Can make this replacement. So if you do that, so let me have this term out. You have this. This is replaced by gamma f a e del psi c. Just keep track of your indices. See, A, B, and E are three indices. So you should have the same here also. A, B, and where is your E? E. A, E, and B. These are three indices. F is dummy. C is contracted. B is contracted. Okay. Similarly, you can change this also. What will be this? Have you done it? Or no? If you have not done it, then let me just write by the same in the same way. You can write this as gamma f db. Xi c x is already there. Del psi d del x. Do you have any problem with this? Are you okay with it? Follow that. Do it. Do it now. Otherwise, you will not learn. Again, একটা দেখিয়ে দিচ্ছি, আরেকটা করো। See, to have a second derivative, you have to replace it by by a gamma times this. না করলে হবে না, গালে হাত দিয়ে বসে থাকলে হবে না। করতে হবে। Step. Good. One person has already completed it. So এসে গেছে। Manjari, you are doing it? হ্যাঁ, ঠিক আছে। মানে এসছে তো? এটা বলে দিন। Good. All the things are got start. Anish. You have to basically use an equation of this form. Appropriately replace the indices to see what will be replaced. This will be the term. I don't want this. Just 1 minute. Huh.
Basically, what we were doing previously was to by hand define a correction. Here we are just defining the transformation between coordinates and relation between the coordinate transformation as the function.
Yeah, see here we have actually defined this expression to be some object gamma d. So the connect and
That means the change of one coordinate with respect to the
we have actually called this quantity as this. Why is, see, the thing is that this quantity you can always say that it is some, because there are c, this is down, so three indices, two below, one on the top, so you define this. And you know that this term should not transform like a tensor. That you know. Because if you look at the geodesic equation, the first term does not transform covariantly under GCT. Therefore, the second term should not transform covariantly under GCT. But combined way, they should transform. All of you have got it? Okay. So if you have got it, now you can see this part, these two terms multiplied by eta CD. And similarly, this and this term multiplied by eta CD, you can replace it by just remove this eta CD, remove this part. This is what? What were the three indices? I forgot.
GFP.
This GFP, very good. Okay. These were only the three indices. And similarly, here also CDs, eta CD, they are contracted. Three indices are X and A and F. Therefore, that is GFA. Very good. This is symmetric. You can write it as GFA or GAF, whatever you like. And therefore, you can see that this minus this is equal to 0. Right? And what is that? That is nothing but nabla E GAB, and that is metric compatibility. So this is equal to 0, but that combination is the covariant derivative of the metric tensor, and that is what we should have. The covariant derivative of the metric tensor should be equal to 0, which is the metric compatibility condition, and therefore that tells us that the metric compatibility condition is basically a physical input. It is the same as imposing the principle of equivalence. So we have given four methods now of getting to the geodesic equation. So let us now, we have learned how to get to the geodesic equation using the variational principle. Let us now solve a problem. Let us consider a curve. Simple problem. Let's consider a curve which is drawn on the plane of this green board, and let us take 2 points on this curve, A and B. Okay, and let the distance be denoted as DAB between these 2 points. What do you think should be the shortest distance between these 2 points? It's a straight line, right? So it should be something like this. Obviously, this curve you can see that its distance should be greater than this. So this is the shortest distance. Let us see whether we can actually find it out from a variational calculation problem. From a variational principle. So this is nothing but ds equal to A to B. Where what is ds? ds is the infinitesimal length element, that is dx square. So this is equal to square square. Then take x common. Okay. This is what we have. Therefore, you can see from this, you can treat this as the action, this distance as the action, and therefore this is something like the Lagrangian, right? And write this as v dx L. And just like you have in classical mechanics, L dt, L being a function of q and q dot. So here your q dot is like dy ds. Okay, this is your Lagrangian L y by prime. So you see that in your Lagrangian you don't have any y, it only has the dot. So this is your Lagrangian. You straight away apply the, you can apply the Euler-Lagrange equation of motion. Please apply it and see what you get. And do it in that way by applying the Euler-Lagrange equation of motion. Or else you can start from first principle calculation. Just vary, take a variation of this, and that will be d dx half this. This so these 2 and 2 will cancel. This is the way you get the Euler Lagrange equation. So dx the variation, assume that the variation and the derivative is commute. This we have this. Now we have to take this outside. Well, this thing did you get any answer? Remember that yes square this way, this right, where y prime is basically your dx. Therefore, dx is this. So you can write this part by down. Did you get any answer? Yes or no? No or yes? Don't have any answer also. Yes or no? So what have you got? What is the final answer? I want the y is equal to mx plus c. So you have got that solution. You have got it. Why are you saying y prime? Everyone has got y is equal to mx plus c. হ্যাঁ সেটা তো পাবি প্রবলেম দেখাই যাচ্ছে তো দিতেই যাবে সব ঠিক আছে এটা তো পাবি তো পড়ার আগেই দেখা যাচ্ছে dx this is ds dx so that dy dx del del x delta y. So this is what this will be a to b dx dy dx into ds ds, so that is dy ds del del x delta y. Now you can write further is equal to d x del del x dy yes delta y minus this is what we have. So this is ddx, dy ds, dx this. This is the total derivative. If you integrate, these are the endpoints. Assume that the variation at the endpoints vanishes. So this term is zero, right? And therefore, and you impose the principle of distraction to extremize the variation, to extremize it, so that delta of d and e is zero. This left hand side is zero. And for an arbitrary variation delta y, immediately there's the equation of motion. So to say dx y. Yes. Get this. And here you can write this dy ds as dy dx into dx ds. So this you can write once again as dy yes dx yes. You put ds dx and solve this differential equation, you will get y is equal to mx plus c. So what you will get basically by solving this differential equation is dy dx is equal to constant. Is it clear? So this was a very simple problem. Now I leave it as an exercise for you to do. Do the same thing, the same exercise on the surface of a sphere and tell me the answer. Basically, you have to find. So these from here we will get dy dx divided by ds dx equal to constant c. You know what dx is, right? dx is what? If you solve, you will get dy dx is equal to constant. That is fine. And therefore y is equal to mx plus c. What does that tell you? It tells you that the shortest distance on a two-dimensional plane is a straight line. So these are the geodesics. Do it on the surface of a sphere. Sphere is what dimensional? How many dimensions are there? Huh? Sphere is only for the fields. It's not for the sphere for the dimension. Three bullets. One, not one dimension. Three. Three. I think not two. It's not there. The answer should not be वो three bullets वो three bullets one three bullets and bullets. हाँ? Three বেশি হবে। আমি ordinary sphere এর কথাই বলছি। Down to earth sphere. Down to earth sphere ই ভালো। Earth sphere is a sphere how to do it. If you think there are whole wallets are big ball, a football. Three. So all of you are three. Sphere equation. हाँ? Let আর উত্তর দেওয়া হয়ে গেছে আর আর ভিডিও কিরা কিরা আর আনে তো নিচে কি বলেছে এটা দেখে হ্যাঁ তাহলে তাহলে কত ডাইমেনশনাল করে এটা কি হোয়াট ইজ ইট হ্যাঁ তাহলে এটা কি আপনি হ্যাঁ তাহলে স্ফিয়ার কত ডাইমেনশনাল কত থ্রি কোঅর্ডিনেট আছে এটা কনস্ট্যান্ট তাহলে তুমি there are only two independent coordinates because z or any of the coordinates you can write it in terms of the other coordinates. So sphere is two dimensional, not three dimensional. It is embedded in three dimensional. Three dimensional space is embedded. It is two dimensional. So plane, this is two dimensional. Sphere is also two dimensional. It's not three dimensional. So now the problem is this was a net problem. That is the problem that you get is net CSI or net option. The big problem is that you find out the geodesics. The same. So you write down the metric on the surface of the sphere and try to solve the Euler-Lagrange equation. From there, try to find out the geodesics. So this is a homework problem. In the last lecture, I gave you a homework problem. I told you to calculate the Hamiltonian, and I'm sure that you have not done it. Devansh. And done. You're not done, right? Anyone? Shubhi? Not done. But you should, I will give you two more this time. So that will be your mid-semester exam. You will be marked on the basis of that portion of your mid-sem. So now you have to do it. না করোনি তো আমি তো টাইম দিয়েছি they're not done and all those guys who are crediting the course they should also do it who are the guys who is crediting তুমিও করো okay you have to do it Sagar you are crediting auditing crediting then you have to do it Anish no credit Anish no credit and তোমার তোমার নাম credit অভিষেক অভিজিৎ কি বন্ধু you are crediting yeah. Say yes or no. Are you ready? No. Then you are P, not to do the problem, but those who are crediting, you have to do it. Okay, so this is also a homework. Please try to figure it out because this is a little bit difficult. And this was a very simple problem. But the sphere problem, you have to do it's a little bit more tricky than this problem. Okay, it's not difficult at all. Now, as I told you, কিছু প্রশ্ন জিজ্ঞেস করো বলো বলো জিজ্ঞেস করো বলো তুমি বলো কি করবো আমি একবার উত্তর দিলাম সাথে কি আছে স্কেল হইলো স্কেল করে হইলো করে আমি স্ফিয়ার যখন বলছি তখন স্ফিয়ারের সারফেসই বলছি সারফেসটাই তো বড় দেখি আমরা সেটা কিন্তু স্ফিয়ার ভেতরে কিন্তু আপনি পুরো স্ফিয়ার না দেখে বুঝতে পারবেন কিন্তু বাল্বের ভেতরে ঢুকে যাবে sphere is defined what by what surface the coordinates x y z coordinates are what these are the coordinates on the surface of this sphere সেটা কিন্তু স্ফিয়ার আর স্ফিয়ার এর ভেতরে যদি তুমি ঢুকে পড়ো তাহলে তার মানে হলো ফুটবলের সারফেসে এটা অরিজিন সেন্টার অফ এটা কোঅর্ডিনেট সিস্টেম অফ অরিজিন থেকে ফুটবলের সারফেসে তুমি কোঅর্ডিনেট মানে বেসিক্যালি যেটা অনন্য লিখেছে ইকুয়েশন ইজ কমপ্লিটলি কারেক্ট you can also write it down in this way r is equal to a is equal to constant right where r is what the radius of the sphere and the radius of the sphere is constant মানে হচ্ছে then that defines the sphere আর the sphere হলো তাহলে তুমি যেটা ভাবছো সেটা হচ্ছে স্ফেরিক্যাল পোলার কোঅর্ডিনেটস এর মতো করে ভাবছো যেখানে সবকিছু ভ্যারি করতে পারে আরটাও ভ্যারি করতে পারে এটাও ভ্যারি করতে পারে আইও যদি যে r is equal to constant বলে দিলে তাহলে তুমি একটা কনস্ট্যান্ট স্ফিয়ার এর উপরেই আছে তখন তোমার r is equal to constant মানে স্ফেরিক্যাল পোলার কোঅর্ডিনেট আচ্ছা দুটো কোঅর্ডিনেট আছে থিটা আর ফাই দুটো রেডিয়াল কোঅর্ডিনেট আছে গুড now just do an important calculation this will take not much time before that okay suppose I told you that if you have a clean vector psi a if you have this clean vector psi a I told you that psi a 2a is a constant along a geodesic. Remember? And I use this result in deriving the gravitational redshift formula using the exact Schwarzschild metric. There I use this fact. If you go back to your class notes, then you will see this. I told you that I shall derive this result for you later. Once I tell you what geodesics are, then I shall derive this result for you. So let us now derive this result. Let us assume that you have some geometry, and that geometry does not change along the x1 direction. So x mu coordinate 4 vector, you have something like this: x0, 1, 2, 3, right? And the metric, what I'm saying is that the metric is independent of one of the coordinates, and that coordinate is x1. Say, let us assume. So what does that mean? If I move along the x1 direction, then the metric does not change. So what will be my killing vector? In that case, my killing vector will be 0, 1, 0, 0. This is my killing vector. So if I move along the x1 direction, this is the x1 direction, the second slot. So if I move along that direction, the metric does not change. And if you remember very carefully, the Schwarzschild geometry, the metric that I wrote down, the class to derive the exact result for the gravitational redshift, you will see that the metric components are independent of time. They were independent of time. So what does that tell us? It tells us that if you move along the time-like direction, then the metric does not change. Therefore, you have a time-like killing vector. So what was the killing vector there? 1, 0, 0, 0. Right? So here I am assuming that the metric does not change along an arbitrary direction and let the direction be x1. So this is my killing vector. A killing vector is a way of characterizing symmetry in any coordinate system. It basically tells you about the symmetries of the problem. Okay. So what does this tell you? It tells us that del L x1 is equal to 0. Because from the metric, I just did a problem, right? What was the problem? The problem was finding the shortest distance on a two-dimensional plane. And what was the metric there? Metric টা কি ছিল? Very good. Metric কি ছিল? Metric was a ds square. ds square plus dy square. It was very simple. The problem that I solved just now, the metric is a two-dimensional Euclidean metric. So if I tell you, ask you to write down the metric coefficients, what will be the metric coefficient? Gxx is 1, Gyy is 1, is a diagonal metric, Euclidean metric, metric components. Sometimes this is some sort of a confusing thing. We call this metric, then we call the metric coefficients as metric. But when I say metric, understand this. If I say G as the metric, then you will understand that I am saying metric coefficients. So here Gxx, Gyy, these are basically metric coefficients. So from the metric, I showed you the way of deriving the Lagrangian of the problem. So given a metric, you can calculate what the Lagrangian is. So if I tell you that the metric does not change along the x1 direction, it means that the Lagrangian is independent of the coordinate x1, right? Because from the metric you can derive the Lagrangian. And if the Lagrangian is independent of the coordinate x1, then del L del x1 is 0, right? And now let us write down the Euler-Lagrange equation. The Euler-Lagrange equation is same. General Theory of Relativity. This is the Euler-Lagrange equation. You have doubts with this. Okay. Like this, I showed you that previous class that write this as here. This I did in the last class when I discussed the variational principle. And from here, you can write this as u tau equal to sigma. This. This was my Lagrange. Okay, that is how, given any metric, you can find out the Lagrangian of the curve. When the curve is parameterized like sigma. Therefore, dt is sigma, d tau is sigma, nothing more than equal to Lagrange. Okay. Let us get back now to the problem that we were discussing. So from that Lagrangian, we have shown already that, so you can think it in this way that L is basically function of dx at sigma. If you treat this as a variational problem, you will end up with this Lagrange equation. So you can actually check it yourself. Okay, so this is equal to 0, and here you note down that A is the D index. So if you apply this equation, which follows from this thing, if you apply, if you just set A is equal to 1 here, this is 1, this is 1. But the metric does not change along the x1 direction. That basically means that the Lagrangian is independent of this coordinate x1. So del L del x1 is 0. This itself is equal to 0. So this is equal to 0 from Euler-Lagrange equation. Therefore, del L del of dx1 sigma constant. This is equal to constant. हम वाला लगा था question. But what is del L del ds1 d sigma? Please calculate it from there. That is your Lagrange. You have to calculate this quantity from that Lagrange. So you have L is equal to GAV dxa dxb sigma and the root. So what is del L del of dx1? That will be obviously 1 by 2 square root of this whole thing, but square root of this whole thing is L, right? Huh?
It is just root G1. You don't need to calculate.
Write it. L আর লিখো না, L লেখাই আছে, L লিখতে হবে।
Where it is. I'm going to consider.
হ্যাঁ সেটাই করো, উত্তরটা খাতায় করো, যেভাবেই করো ওইভাবে ভেঙে করার দরকার নেই। আচ্ছা, প্লিজ ডু ইট। And this, remember that this is equal to constant. This is a constant. So if I differentiate L with respect to ds1 d sigma, I will get 1 by 2 Lagrangian. And from here, you have to just differentiate this with respect to this factor, right? dx1 d sigma. So what I did, I isolated, I put this to be 1. Then you will get 1. And you don't need the other coordinates because the other coordinates they are 0. So only 1b dx1 d sigma dxb d sigma will be a factor of 2 because you could have set this also as 1. And this is symmetry. So you will get factor of 2. So this 2 and 2 will cancel out. We have g1b dxb d sigma. But that is equal to g1b dxb d tau d sigma. Right? This is dxb d sigma chain root d tau d sigma. What is d tau d sigma? From here, d tau d sigma is L. So, and you have a 1 by L obviously here. This is also L. So L and L also cancels. So what you have is G1B dxb d tau. And what is dxb d tau? That is UB. This is G1B B. Is it okay? So what have we got now? We have got following result that G1B UB is equal to constant. But this thing you can write the same thing as GAB. This is the same as this. G1B UB is the same as GAB Xia UB. Why? Because GAB Xia only one component. Xia, if you remember Xia, what was Xia? So only the one component is, all are zero. So if you sum G is 0, Xi is 0, Xi 0 is 0, 2 is 0, 3 is 0. So only one will survive. So 1, 1. So this G1B you can write it down as GAB Xia. Therefore, you can put by this metric, you can lower the index down. So Xia UA is equal to constant along a geodesy. Why along a geodesy? Because we have derived this full thing from the Euler-Lagrange equation. Euler-Lagrange equation means geodesy. A path which satisfies obeys the Euler-Lagrange equation, which you get by solving the Euler-Lagrange equation, must be a geodesy. Therefore, Xia UA is a constant along a geodesy. If Xia is a time vector, is a killing vector. By killing vector, we mean that it is a direction along which the metric does not change or the Lagrangian does not change. So this is a constant. This is the result that we used while deriving the gravitational redshift on the Schwarzschild geometry. So we have proved this result. Do you have any questions? I cannot hear you. Put your mask.
We have proved it for x direction, but the result that we get is completely
Completely general. This I just assume that let one of the direction be x1. The direction can be anything. Nothing to do with it. It was just arbitrary. X1 is an arbitrary direction. Can be x2, x3, x0. It's completely arbitrary. Let's take a break of 2 minutes. So you can question yourself. Then we will start. So afraid of should mask when you're outside. Then you should wear the mask. Let's take a break of 2 minutes and then we shall start. So if, at this point you can ask any questions if you have any doubt in your minds. So thing that I should like to discuss with you the following. Let us go back to Newtonian gravity. And in Newtonian gravity, you know what is the expression, what is the equation of motion for a particle moving in a gravitational field, gravitational potential. So we have got all the derived the important equation, which is known as the geodesic equation. But you can ask the question that okay, this is fine, but in Newtonian mechanics, you know that there is the following thing, right? For a for a, for a particle being in the gravitational potential, you should have this. This is the equation of motion. And important thing is that this the important thing is that phi is vector. Right? This is Newtonian gravity. The equation of motion is this. The particle moving in this gravitational potential. So now the question that one can ask is the following. If the geodesic equation represents the equation of motion of a free particle in a gravitational field, then in the appropriate limit, by appropriate limit I mean the non-relativistic limit, it should go back to this equation. Because this equation, in all the planetary motion, everything works, you can explain by using this equation, and this equation, and with this gravitational potential. So in some appropriate limit, your geodesic equation should go back to this. This is what you should expect. Let us see whether this happens or not. So what we shall do is, here you should just note it down. The assumption is that we assume the gravitational field to be weak and the metric changes slightly from the Minkowski metric. This is what we assume. The gravitational field, we assume it to be weak. We assume the gravitational field to be weak and the metric changes very slightly from the Minkowski metric. This is our assumption, or you can say this is our approximation. This is known as the weak field approximation. So what we do, we know that this is the metric, right? This is a full curved metric tensor, and this describes the gravitational field. By now we have learned that the metric tensor basically describes the gravitational field. So we assume that it changes very slightly from the Minkowski metric. So this is the weak field approximation, where HAB is small. It's assumed to be small in magnitude. So this is so if we have this, obviously eta AB is a constant, GAB is a function of x, is a function of this external coordinates. This is a constant, this is a function of x, this must be a function of x. So immediately what we should do is calculate the inverse of this. So what will be the inverse of this? And we shall keep terms only up to first order in H. This is our approximation. To this approximation we are working. Right? So this will be what? This is the AB. Very good. Okay. It's approximately to this order. Why is this true? Because GAB, GD, let me just use the indices that I have used. I have used C. So this should be equal to delta AC. Okay. Please check. Put GBC to be equal to this and GAB to be equal to this and check this. Let us check this. Whether this is indeed true. Because this must be true. Whatever, whichever order you are working, whatever order you are working, you could have worked up to order h square also. Whatever order you are working, this must be true. What does this tell you? If you contract these indices, unless A is on top, this must be the one delta. Because this and this are inverses of each other. So this must be the identity matrix. So it is independent of the fact whether you are working with approximately or exactly. Good. So to do this, you can immediately see that GAB is basically theta AB minus HAB times GBC is theta BC plus H. Let us carry out the multiplication. Theta AB into theta BC, that is delta AC, the first term. This multiplied by this. The second term is minus H AB theta BC. Third term is this multiplied by this, which is theta AB H C. The fourth term is order of H square. So we are not keeping terms up to order H square, it's up to order. This expression is accurate up to order H. So we shall neglect all terms up to order H square. Now what is HAB theta BC? Theta BC is the metric tensor now, which will be used to raise and lower indices. So what it will do is it will EB. So what it will do?
You will
HAC. Similarly here, we raise it HAC, this cancels. Therefore, to order H, this is equal to this. Therefore, this is indeed the inverse. G contravariant AB is indeed the inverse of G covariant AB. Okay, good. Also, we shall assume that the gravitational field is stationary. So it is independent of time. The metric is independent of time. So if you assume that, then you will have del naught GAP is equal to 0. This would imply that del naught HAB also equal to 0. Because HID is already independent of time. And we shall take the non-relativistic limit. The non-relativistic limit tells you that this basically tells us that dxi dt dxi d tau inside without is much less than. This is the non-relativistic limit. This basically tells you that the particle velocity is much smaller than the speed of light. Please check it. You impose this condition and try to convince yourself that the particle velocity is smaller than the speed of light. Okay. If you have all these things, so you have made this approximation, this is the weak field limit. This is the second one. You are assuming that the gravitational field is independent of time, and you are assuming that the particle velocity is much smaller than this. Now let us write down the geodesic equation. This is the geodesic equation. So here, from this term, now we shall impose all the approximations that we have. So from this term, you can immediately see that there will be terms gamma A I, which will give you dxi d tau, C j dxj d tau. There will be term where you will have 0 dx 0 d tau dx 0 d tau, and the I terms will be smaller than dx 0 d tau, right? So you can basically write this down as gamma, approximately gamma is 0. So we have imposed the first approximation that the particle velocity is much smaller than the speed of light. So that is the non-relativistic approximation. So this is NR. This is the non-relativistic limit. So if you impose the non-relativistic limit, just expand this thing, impose this thing. Only the time components survives. So let us now concentrate on gamma, calculate what gamma A00 is. Please tell me the expression for gamma. I always forget these expressions. So gamma APC is equal to half GAE. Then G. Now I have to look at the indices. There is GAE. Follow the group. Del not delta. Del D. D is Yago. Please check whether I am writing it correctly or not. Whether this is the correct expression or not. Is it correct? Huh? Ankur? I can rely on Ankur. So this is correct. This is correct. So GAE P is fine. So from here we have to calculate A 0. This is equal to half GAE. B is 0, so this is 0. B is 0 plus L 0. G is once again 0 minus B. Right? Now comes the second approximation, that is the gravitational field is stationary. It is time stationary means time independent. This is 0, this is 0. Therefore, this is minus half G E. This is what we do. This is G00, right? Okay. But so we have imposed on the geodesic equation for the particle moving in the deep gravitational field. We have imposed the non-relativistic approximation. This was non-relativistic approximation. Now we are calculating this. In calculating this, we have used the stationary field approximation. That the gravitational field is independent of time, so you get this. Now we shall input the last approximation. What is that? The weak field approximation, which says that the gravitational field is slightly different from the Minkowski range. So G00 is what? Is eta 00 plus H00, eta 00 is 1, so it's constant. So derivative will be 0. What is GAE? GAE is 1/2 eta AE minus H. So this is also the big field approximation. This. Now we are working up to order H only, not we are throwing out terms of order H square. So in that approximation, approximately minus half that T T H 0. This into this is order H square. So throw it out. So we have imposed all the three approximations. Now let us calculate what gamma 000 is. Let's calculate this. So this you can immediately get it from this equation that we have obtained minus half theta 0 E del E H00. But this is sum over E and this is diagonal, right? This is diagonal matrix. 0 I are all 0, eta 0 I is 0. Okay? This only component which survives is this. And what is del 0 of H00? Again stationary, so it is 0. This component is here. Let us calculate what gamma I 00 is. This is nothing but put this is the free index, so you put A is equal to I E del E 00. And you can write this if you like. Half theta is used to this. If you like, you can write it like this. If you don't like, you cannot write it like this. What this basically means is that you have to now look at I is 1, 2, 3, right? So you can calculate what gamma 100 is, gamma 200 is. That way you can calculate. So gamma 100 will be eta 1 E. So again, this is diagonal matrix. So eta 1 1 should be on eta 1 1 del 1 800. This is what we have. Now we have all the components in our hands. Remember that gamma 00 this is 0, so I'm rubbing this out. You don't need this one. The only non-trivial gamma is this. This is non-zero. So if we have this, let us write down, go back to the geodesic equation. What was the geodesic equation? V2 x8 d tau 2. Under the non-relativistic approximation, we had shown that the geodesic equation is this was the geodesic equation dt d tau whole square. So let us put a is equal to 0 first, because a is the field index. This equation we got under the non-relativistic approximation, right? Now set a is equal to 0. So if you set a is equal to 0 in this geodesic equation for the particle, we immediately get what? Because gamma 0 is 0. Huh? Yes. That is what you are getting. Proportion. Constant you can always throw it out. It's just scaling. So this is the equation of motion for this key. That is what you are getting. Just solve this equation and see what happens. So dx0 d tau is constant. Therefore x0 is tau plus c. So x0 is t and tau. Fine. Let us. So this implies that we just write it down. This is what a is equal to 0. Put a is equal to I. Let us put a is equal to I now. So we have this part. So if you put a is equal to I, which is the field index, we shall get d2xi tau 2 plus gamma I cube dt d tau is equal to 0. Okay. But from this equation, know that dt d tau is constant. And let me put what del gamma is equal to is. Gamma is equal to, I will write another line. What I will do is just put minus half del I in place of gamma in 0, 0. So this is my geodesic equation for the spatial coordinates, right? Therefore, you can write, now you can use the vector notation, right? Yeah. I means you can just change to the vector notation. This is tau 2. That is equal to half
Data is red.
yes, that is what I should write. Okay, wait. It is not good to write it at this stage like this. The idea I will change it later. What is the signature that we are using? It is mostly positive. So since it is mostly positive, therefore write this. Just put it down. Right? Now you can safely there because del I downstairs is basically the gradient operator in vector notation. B. There is my Here. Very good. So you have got this as the equation. Tau d tau. This is a constant. So c square. You can write this also. d tau. Dx vector d tau. That is dx vector dt d tau. This is again a constant. The constant. So one constant cancels with c square. So you only have a single constant on that side. This dd tau is again dt d tau. That is again a constant. So both all constants cancel. So ultimately what we have is d2x 2 equal to half. Oh, is not there. That is. So this is the equation of motion that you get. This is the equation of motion of the particle moving in a gravitational field. Free particle. Equation of motion of the free particle moving in a gravitational field. So let us now write down the Newton's equation. So here, if this geodesic equation represents the equation of motion of a free particle in a gravitational field, then it must reduce to the Newton's equation of motion in the appropriate limits, in the non-relativistic limit. So if that is true, then you can compare this equation with this equation. If you compare this equation with this equation, you will get half that is 0, 6 function of x vector equal to minus gradient, where phi x is what? Is the gravitational potential. So this equation we get by comparing this with this, the right hand sides. This is what we get. And take that 2 on the other side. This is 2. Therefore, now if you integrate, we get 800 function of vector equal to minus 2 phi function of this vector plus some constant of integration. How to fix the constant of integration? Huh? How can you fix the constant of integration? See, this is a weak field limit. You are come on. So it should not G00 should be flat. So what is G00? G00 is obviously function of x, theta 00 plus B 00 function of x. So if you are far away from the source, then this gravitational field that you have, the curved nature of the geometry that you have in the source, that should go to the Minkowski. So H00 should go to 0, right? So for x going to infinity, for mod x vector going to infinity, phi x is what? Phi x is this. For x going to mod x going to infinity, phi x goes to 0. And H00 should also go to 0 because the metric should go to the flat metric far away from the source. So it should go to eta 00. So because this should vanish so that this goes to eta 00. And therefore this is 0, this is 0. For mod x means there's a constant is 0. We fix the constant. And therefore, is we are working with mostly positive signature, right? So eta 00 is what? Minus 1. H00 is what? Minus 2 phi x. This is equal to minus 1 plus 2 phi x. And that is equal to minus 1 minus 2 g. Is this fine? And therefore, if you want to write, see, by, by this exercise, what we have found out is we have obtained one of the components of the metric, the G00 component, we have actually obtained by comparing the geodesic equation in curved spacetime with Newton's theory. So we have not really solved the dynamical equation. Obviously, the geodesic equation is a dynamical equation, but this is a dynamical equation for the particle moving in a background geometry. I give you a geometry, so it is like the geometry tells the matter how to move. So if I give you a geometry, then you know how will the particle move in that geometry. So that is given by the geodesic equation. So from that equation, if you compare that equation with Newton's theory, you are able to get one of the components of the metric immediately, the weak field. And that is all that we can get by comparing this idea of curved geometry and gravitational field, or the idea of Einstein. That is what you can get by comparing Einstein's theory with Newton's theory. So you have actually determined one of the components. And this is our task, right? We want to determine the components of the curved spacetime. Our whole task in general relativity is to determine the components of the metric, or determine, in other words, determine the metric coefficients. That is what all we want to do. And here, by this exercise, we have defined that G00 is basically this. And go back to Schwarzschild geometry. See what you got there. The G00 component was basically this. Because this mod x is nothing but r, right? It's a radial distance. So it is 1 minus 2 gm by r. So outside the source, the 00 component of the metric is basically this. And that we have already obtained by comparing Einstein's theory with Newton's theory. But what about the other components? Those components you cannot get. Those components we have to do something else. That's something else we have to do in the future classes. So, and what is also important here, if you remember that this was the only component that we required to derive the gravitational redshift. This was only required. So we have derived this also. The 00 component of the Schwarzschild geometry. We have derived it. Not the full Schwarzschild geometry, but the 00 component, a part of it. And this was what was all required to derive the gravitational redshift. Good. So I think it is a good place to stop here for today. We shall continue from here on Monday. So if you have any questions, you can ask me at this point. Because in the next lecture, we shall start doing curvature. We have almost all the ingredients required to discuss what curvature is.